Hello, everyone, and welcome to phyloseminar.org, a project supported by the Society of Systematic Biologists. I want to remind people that if you have questions, you can submit them via the Questions app. So that should appear as an option on the left sidebar if you scroll over. So today we're in the middle of a series on ancestral recombination graphs and phylogenetics. First, we had Matt Rasmussen. And now we have Peter, which is awesome, Peter Ralph. And then next we're going to have Matthias Steinrücken. So Matthias has recently changed the time of his seminar to be on March 5th. So that's updated on the website. Right, so today we have Peter speaking. Peter did his PhD with Steve Evans at Berkeley, and then went over to Davis and worked with Sebastian Schreiber and Graham Coop, and then is now faculty at USC, where he's doing lots of cool stuff. So I'm very excited to have you, Peter.
Thanks, Eric. I'm also excited to be here, and I guess by here I mean my office, but also in the really great pilot seminar. Can you see my screen?
Yep, looks great.
Oops, but I'm not at the start of the presentation.
There you are.
So, I'm pleased to be here in this virtual place. I guess like Matt, I'm going to be talking about the ancestral recombination graph, but just to make sure we're all on the same page. What I mean by that, so the ancestral recombination graph, or ARG, is sort of both the pedigree, which is the thing that tells you, like for every individual alive ever, who their parents are. So in addition to that, all the genetic relationships within that. So you could think of that as the outcome of every recombination. Okay, and there's several equivalent ways of thinking about that. One is that the ARG tells you for any particular individual, and I guess so. In this whole talk, I'm going to be thinking of individuals as haploids. So think of individual chromosomes. For any particular individual, you can look back to any further back point in time and see from which ancestors has that chromosome inherited which parts. Okay, so how that chromosome is sort of broken up amongst its ancestors in terms of who it's been inherited from. So that's one way of thinking about it. Another equivalent way is that you can look at any particular point on the genome and see the gene tree at that point. So at a particular point on the genome, it's a tree that relates everybody, and you can see what that marginal gene tree is. Okay, and sort of originally, I guess Griffiths and Marjoram introduced this terminology and this way of keeping track of things called they called it, I guess, an ancestral recombination graph, and that was in the context of. They introduced it as a stochastic process that sort of extends Kingman's coalescing to the case with recombination. So what all the genetic relationships look like in a large randomly mating population. Okay, but what I want to think about today is sort of the realized ARG. What I just said is something that actually happened in any population. There is some true sequence of events that happen that we can't actually observe, but exists. And I'm going to call that the realized ARG, and that's the sort of the thing that I want to think about. And of course, the genomic data that we get to see is the result of mutations that have occurred in the context of this ARG, right? The ARG determines, tells us who has co-inherited different mutations, and thus where different sequences differ or not with each other. Okay, so I'm going to start out with a quick example that is not novel and is probably pretty obvious, but sets the stage for the more general stuff that I'm going to talk about later. So just for the sake of argument, let's suppose that we know the genotypes of the entire population some very long time ago, okay? And we know the ARG, going all the way back to that time, okay? So that almost also tells us the genotypes of everybody in the population today, right? Because for any bit of their genome, we can go look at, well, who did they inherit that bit from, and what was the genotypes of the ancestors, okay? But the thing that we don't know is what mutations might have occurred since that time, okay? But given that information, if we assume that mutations are neutral, so sort of knowing the ARG doesn't tell us anything about where mutations are likely to have occurred, we can sample from the distribution on observed genotypes. So here's an example picture of this. Down at the bottom, I'm going to sample from 2 genotypes today. What I'm showing you right here is that here's their gene tree at this first location on the genome. They share a common ancestor fairly recently. They've both got an A that they inherited from some ancestor a long time ago up at the root of the tree. Okay, and at the next site, the gene tree is the same. They both have a T there, which turns out to have been from a mutation that happened somewhere along their lineage, but prior to their common ancestor, and in the ancestral population, there is a C there. And you can march along the genome like this, like looking at each subsequent gene tree and laying down mutations on it. And at some point, the gene trees will change because of recombination. And eventually, we'll get to sites where the 2 sequences differ because a mutation has occurred on the gene tree since the most recent common ancestor of the 2 sequences. And you can proceed like that. Okay, and now if you forget about the ancestral sequence, so just what we get to observe is the modern day sequences. You see that the places, the opportunity for these 2 sequences to differ is determined by sort of the total area of, this area of the ARG. I'm moving my mouse around it, but in case you can't see, it's the total lengths of the gene trees up until the most recent common ancestors, right? Because those are the places where if a mutation did occur, the 2 sequences would differ. Okay, so what this is saying is, suppose that we calculate sequence divergence between 2 samples. So sequence divergence between samples X and Y across some set of sites is 1 on the number of sites times the number of sites that they differ at. If we ignore double mutation, so assume no 2 mutations land in the same site, like I'm going to assume for most of today, then this is just equal to the number of mutations that have occurred sort of on those gene trees since their most recent common ancestor divided by the number of sites. And if we get to assume that mutations are independent of the ARG, then it's reasonable that the sequence divergence, that number of mutations is Poisson, with mean equal to the sum across sites of the mutation rate at the site multiplied by the length of the path connecting the 2 samples at that site. Okay, so this is the notation here. Mu I is the mutation rate at site I, and Ti is the length of the path between X and Y at site I. So that's measured in number of diocese. And you can think of that as twice the coalescent time at that site. And sort of informally, I'll think of this, I'll refer to it as the coalescent time sometimes. So what this implies, and it's kind of kind of obvious maybe is that if you think of the arg as given, the expected value of sequence divergence is the empirical mean mutation-weighted length of a path between the two sequences. So the empirical mean mutation-weighted coalescent time between the two sequences. Okay, that's what this first quantity is. And since the number of mutations is Poisson, the variance is just the same thing divided by another factor of I. Okay, so then concretely, concretely we could think of sequence divergence across a set of sites as being sort of an estimator of this empirical mean coalescent time. And we have a concrete idea of what the sort of standard error of that estimator is. You know, how close do we expect to be this thing that we estimate from mutations to the actual quantity in terms of the realized arg. So I just now want to point out, like here in this last slide, I'm writing an expectation and a variance in sort of a different way than I might usually as a population geneticist, because often I'd be thinking about a stochastic model of demography, like with Kingman's coalescent. So it would be more usual to say that suppose we have a large randomly median population of size 2n, in which case the mean sequence divergence is 4n times the mutation rate. So that's actually the same thing as our previous result, which I've got down here, because the mean coalescent time under that model is twice n. Okay, but then the variance is the variance of the sequence divergence under Kingman's coalescent is this much more complicated thing that depends on recombination. And in particular, it's strictly greater than the variance that I just wrote down because it includes averaging over demographies. Okay, so it means really a different thing. Okay, so this is just, I'm just pointing out the difference here. And one more sort of note here before I move away from this first example, which is that you know, what I said was that the sequence divergence is basically, it's one on the number of sites, but then multiplied by a Poisson random variable whose mean is a function of this mean coalescent time, right? Which is sort of this total area, like mutation-weighted area of a chunk of the arg. So what that means, because it only depends on that, like of all the aspects of the arg, it only depends on that. It means that if we try to do, you know, probably inadvisably, but this is for the purposes of illustration, suppose that we're trying to do demographic inference, only using sequence divergence, or maybe a collection of sequence divergences between some samples. Okay. What that means is that because the sequence divergence only depends on the arg through this quantity, that whatever demographic model we use, the only thing that matters about that demographic model is the distribution it induces on the mean coalescent time. Okay, and here I've got, you know, I'm writing down, you know, that the only thing that would enter into the likelihood is effectively, you know, here you could move this over into the distribution that the your demographic model induces on the mean coalescent time. Okay, and then what that means in practice is that the demographic models that we, the different parameters of the demographic model that we're trying to infer are only distinguishable, like insofar as the distributions they induce on the pairwise coalescent time differs. Okay, so okay, so that was sort of the setup to hopefully put you in the right context. And now I'm going to, so now the goal of this talk is sort of to think about how to do that same thing, to understand population genetic statistics on that sort of level, as, to understand what they tell us about the realized ARG, more generally, to do that for more general statistics. So first I'm going to present some abstract stuff to be able to do that. Then I'm going to apply it to a more complicated statistic, but that's still a single site statistic, and then I'm going to talk about how to do this also using recombination. Okay, so just to remind you, often in population genetics, we put models on the mutation process, on the recombination process, and also on demography. So in no part of this am I going to put a model on demography. And in the first part, I'm not going to put a model on recombination either. Okay, I'm just going to think about the noise introduced, or the information introduced by mutation, and which I'm going to assume is neutral. Okay. So so the data that we get to see is a result of mutations that have happened somewhere on the ARG. Okay, and so let's say that a mutation happens on a particular ancestral genome. If that ancestor differs at that site from the parent that they inherited from. Okay, so there is an error or whatever in the meiosis leading to that ancestor. Okay, so this means that mutations are we can think of them as being located on ancestral genomes, and when we think about the ARG, we want to think about the genomes of everyone alive ever. Okay, so so I want to think about the mutation process as being a Poisson process on the genomes of everybody alive, the genomes of everyone alive ever. Okay. So what this does is, for any collection of pieces of ancestral genomes, we can count up how many mutations have occurred in total on those pieces. And then furthermore, that number is Poisson with a mean that's equal to the sum over those genomes of the mutation rates. Okay, and it turns out to be useful to be able to integrate test functions against this mutation process, lambda. So big lambda here is the mutation process, and I want to define a test function on ancestral genomes to integrate against it. So by a test function, I mean a function that I can give to it a bit of ancestral genome, so tell it like where on the genome it is and in which ancestor, and it gives me back a real number. Okay. And don't worry, I'll have a concrete example in a sec, but what it means to integrate a test function against the mutation process lambda is just to sum up the values of that function evaluated at all the mutations that have occurred. Okay, so so in particular, phi is the test function. Phi better be 0 most of the time, or this is going to be, a really big number. And associated with this, with the mutation process, is a mean measure. Okay, that just tells you, so the mean measure tells you for any chunk of ancestral genomes how many mutations you expect to see in that chunk. Okay, so, and I'm assuming here that that just depends on which site it is. So the expected value of the integral of a test function phi against the mutation process, so the integral against the mutation process is a random quantity, but its expected value is just the integral of that test function against the mean measure. So you sum across all sites in all individuals, and you multiply the mutation rate at that site times the value that phi takes on at that site. Okay, so it's abstract. Here's a quick, useless but illustrative example. Let's suppose that we wanted to count up the number of new mutations that some particular individual, A star, has, so places where they differ from their parents. So to do this, we could define the test function phi to be 1 on the genome of that individual, A star, and 0 everywhere else in the whole ARG. Okay. So then when you integrate phi against the mutation process, remember that just means that you count up, you look at all the mutations, multiply them by the value of phi. Since phi is 1, that means just counting up all the mutations that have occurred in this individual. All right? And then, of course, the expected number of new mutations in this individual is the integral of phi against the mean measure, which is just the sum of the mutation rates across the genome. Okay. So here's another example of a test function that we might want to use. So that this is the thing that would come up in the example of pairwise sequence divergence. So I want to define this function. So I'm saying that x and y in brackets with arrows between is a indicator function, is a test function on the ARG that I call the path from x to y. I'm going to define it to take the value 1 at a bit of ancestral genome if either x or y have inherited that bit of genome, but not both of them, and 0 otherwise. So 0 if neither x or y have inherited that bit of genome, or if both of them have. So on the right here is sort of a picture of what that function looks like, right? It's +1 on the path from x and y up to their common ancestor, and 0 elsewhere. And of course, this is a picture of the marginal gene tree, and what that gene tree is varies along the sequence, but it always, up to topology looks like this. Okay, so if we integrate this test function against the mutation process lambda, what we do is we just count up the number of mutations that were inherited by x or y, but not both of them. Okay. Which is exactly what we were looking at above with sequence divergence. And when we integrate, the expected value of this is the integral against the mean measure, which is the mutation-weighted sum of the path length between x and y, right? Or the total length of the tree between x and y, if you'd rather. Okay, so here, this is a way that we could do the previous computation in a more complicated manner. Great. But I still claim it's useful for extending that to other things. So let's suppose that we have some actual genotypes. Let's say GXI is the genotype of some individual, so a haploid individual. And let's suppose that we've polarized these things so that 0 is the ancestral genotype defined somehow, and 1 is the derived phenotype. The derived genotype. And a lot of these statistics that we want to compute involve taking the difference of two individuals' genotypes. And now what is that in these terms? So what we want to do in terms of counting mutations is that a mutation that happened on the branch from X up to the common ancestor would make this quantity, would make this difference in genotypes, the genotype of X minus the genotype of Y, equal to +1. And a mutation occurring on the branch going from Y up to the common ancestor would make this -1. Okay, so that sort of motivates defining this other thing that's like the path from X to Y, but I'm calling it the flow from X to Y. So it's a test function. It's a function on the arg that takes the value +1 for any bit of ancestral genome that was inherited by X but not Y. It takes the value -1 for any bit of ancestral genome that was inherited by Y but not X. Okay, and is 0 everywhere else. And so if we integrate the flow from X to Y against the mutation process, we count up the number of mutations that Y has, that X has and Y doesn't, and subtract the number of mutations that Y has that X doesn't. And its expected value is the sum across the genome of the mutation rate times sort of the asymmetry of the gene tree at that point, the difference in the two branch lengths. Okay, and one more abstract definition here. So just now I defined what the flow from X to Y is, and I want to be able to define the flow from a group of samples to another group of samples. So if big X and big Y are groups of samples, say like big X has 2 samples and big Y has 3 samples, then we can define the flow from big X to big Y as the average across the flows from between each pair, right? So for any pair of individuals, one chosen from X and one chosen from Y, we have a flow between them. And I want to add up all those flows and divide by the total number of pairs. Okay, so here is, on the right, thinking of these things as functions. This is just their definition. And then up here is a depiction of what values this function takes on those parts of the arg at which this is the marginal gene tree, right? It won't look like this at all parts of the genome, but on bits where X and Y are monophyletic, this is what it looks like. Okay. Okay, and that'll be useful in a minute. Now, sort of the reason that this formalism of defining test functions on the arg is useful is because it's easy to compute things for them, right? Because we have down here this general formula that tells us, gives us an exact formula for what the Laplace transform of the integral of a test function against the mutation process, against a Poisson process is. Okay, and just by differentiating that, we can get, for instance, these two simple formulas for what the mean and the covariance of two such quantities is. Okay, and so those are the tools that we can use. If we can formulate a statistic in terms of one of these integrals against the mutation process, then we can sort of compute whatever we want about it. So here is here is just saying the same thing about sequence divergence, and I think of unless somebody says something right now, I think I'll skip this.
No problem. No problem.
Okay, great. And move on to the more the more complicated statistics. So So this is so I want to think about the F4 statistic. And it was sort of introduced to look for introgression of Neanderthal DNA into Europeans. The best reference to see what it is Patterson et al., where they introduced admix tools. And I should say up front that when they actually compute the F4 statistic from data, there's a couple of extra correction terms that they put in here that I'm leaving out for simplicity, but this is almost exactly it. So what the F4 statistic is suppose that we have two pairs of populations, really, U and V and X and Y, and we have a bunch of samples from each of those, one or more samples. Okay, and the motivation is that we sort of think that that mostly the marginal gene tree, it looks like this thing on the right, but then we're wondering if there's introgression from X into V. So imagine that U is African, V is European, X is Neanderthal, and Y is chimpanzee. Okay. And so under the null hypothesis of no introgression, right, you see U and V are symmetric. So switching U and V should not change the value of the statistic. Right, but then you'll see in a minute when I explain what it is that switching U and V changes the sign of F4. So therefore, under the null hypothesis, the statistic, the expected value would be 0. Okay, and then sorry, what the statistic actually is that you average across all sites of the allele frequency difference between U and V multiplied by the allele frequency difference between X and Y. Okay. Right, so when you switch U and V, you get a minus sign, and that means that sort of the expected value under the null of no introgression is 0. So that's why it's a test for introgression. Okay, but then it'd still be nice to know, like, what does this actually mean? Okay.
Sorry, Peter. I'm a little confused.
Yeah.
You have any headphones handy? But in any case, I don't see why this asymmetry with respect to U and V tells us that this is an introgression statistic.
Well, are you convinced that if there was no little red arrow there, then the expected value of the statistic would be 0?
Yes.
Okay, so then if we compute the statistic from data and get something that's not 0, and also have a method for estimating confidence intervals on what it is, then those confidence intervals exclude 0, then that's good evidence that there was introgression.
Okay, just that there's some sort of model violation, I guess.
Right, yeah, I mean, like, there are other situations that you could draw which would lead to, making F4 positive, other than this tree, but, in the, when it's applied, often you have a pretty good idea, like with the human Neanderthal example, of what the tree mostly is, right?
Cool.
Or I should have said what most of the trees are. Okay?
Got it.
All right. Yep, we're all good?
Yeah.
Okay, right. So, so at this point, I should say, okay, just believe me that it's useful, and that would actually like to understand it better, maybe. So these PIs here are the empirical frequencies among our samples. Okay, so I can sort of pull out those averages across the sample genotypes like this and write the F4 statistic as the sum across sites, or sorry, the average across sites of the average across choices of 4 individuals, one each from U, V, X, and Y, of the product in differences of genotypes between the individual from U and V and the individuals from X and Y. Okay, and sort of, if you were convinced before that that a good way of writing the difference in genotypes was the integral of the flow, so that a good way of writing the difference in genotypes between U and V was the integral of the flow from U to V against the mutation process. Then it should seem reasonable also that the this sum across all sites of the product in differences of genotypes we can write as the integral of the product of flows against the mutation process. Okay, and then this is sort of why I introduced the flow from one group to another, because if we put these averages over choices of individuals back inside the integral here, we get that the F4 statistic is 1 on the number of sites times the product of the flow from U to V with the flow from X to Y integrated against the mutation process. Okay. And now that's something that we can use the formalism to compute things about. Okay. You know, recall that before we had explicit expressions for the means and covariances of 2 test functions, so we can use that. It turns out that the expected value of the integral of the product of these 2 things is equal to the integral of their product against the mean measure. This is, I think I should have said, but this is assuming there are some other terms, but if we assume that the that U and V are contemporaneous, then this holds. Okay, so great, but what does this mean? Okay, so recall up here, on the right here, we've got the picture of what the flow from a group X to a group Y means. Okay, so you can sort of see from this picture that the value that it takes at any particular any particular chunk of ancestral genome is the proportion of the samples in X that have inherited from that bit of genome minus the proportion of samples in Y that have inherited from that bit of genome. Okay, so that's what I've got here. That the flow from U to V is the proportion of the samples in U that have inherited from that bit of genome minus the proportion of samples in V. Okay, so what this quantity here is, the expected value of the F4, is equal to 1 on the number of sites times the sum over all ancestral genomes of the mutation rate times the product of differences of you know, the proportion of U inherited, the proportion of U that have inherited from that bit of ancestral genome minus the corresponding thing for V. So it's sort of multiplied by the same thing for X and Y. So it's sort of an empirical covariance of differences in proportions of genomes inherited. Okay. So this is still a little bit hard to get your head around, but the nice thing about it is that it's a concrete thing that makes sense sort of regardless of your demographic model and regardless if you sort of implicitly assume that the true phylogeny of the populations is mostly tree-like or anything. Okay. And we can also work out what the variance is. It's something similar. Okay. Okay. So now, unless there is, yeah, unless there's a quick question, I'm going to move on to talking about recombination. Okay, so so far we've just been thinking about single site statistics, right? Sequence divergence and this F4 statistic just summed across sites and didn't use anything about, more than one site at once at all. Okay, so in terms of thinking about something using recombination, right, there's a lot of information there in recombination potentially in organisms that do it. But it's also kind of harder to get to because recombination is sort of less directly observable than mutation. Okay, so I'm going to look at the IBD block length spectrum. And just to get everybody on the same page, here's what it is. And hold on. Eric, am I aiming to end at 10:50 or at 11?
10:50 is best.
Okay.
Yeah. And I thought I might also mention, you pointed out that IBD stands for identity by descent.
Right, that was going to be my next sentence, if I remembered. Thank you. But I probably wouldn't have. Okay, right. So, so here's a picture that I probably should have put up earlier, right? This is a bit of the pedigree. Down here at the bottom are two cousins, and up here are their grandparents. And what we can see of sort of colored in the grandparental chromosomes, and then we can see how their offspring and then these two cousins, their genomes are composed of a mosaic of these of the grandparental chromosomes. Okay, and what you can see maybe is that those two cousins have both inherited a bit of the same red chromosome from the same grandparent. And so that piece there, like that chunk, we call we say that it's been inherited identically by descent, or it's an IBD block, because it's been here, in these two chromosomes, it's been inherited without recombination breaking up along the way from a single common ancestor. Okay, so we could go through and segregate, take their two chromosomes and divide the entire chromosomes up into chunks of IBD, right? Because at any point, any two individuals share a common ancestor. Now, most of those chunks of IBD would be really short and really old and would have no chance of telling what they are, but it sort of turns out in practice that you get enough relatively long ones that you can identify sort of over the background. So IBD blocks are something that are, sort of not observable, but in practice sort of are, at least statistically. So so this is a useful thing, and it's really useful for getting intuition about how this works. Okay. The statistic I want to use is the IBD block length spectrum. So by that I mean, suppose I've got two groups of samples, X and Y. I'm going to define block length spectrum to be this function B of L, to be the mean number of blocks of IBD having genetic length at least L that are shared by a pair of individuals from X and from Y. Okay. And this sort of tells us about the relationships between the two groups, because the more long blocks they share, the long blocks must come from recent common ancestors, because there's been less chance for recombination to break them up. Okay. So if this is our statistic, we can't hope to learn anything from it, of course, if we treat the ARG as given, because the ARG determines exactly what the IBD blocks are. Okay, so we have to put a model on recombination as well as mutation, but we can still treat the pedigree as being fixed. Okay, so so now we want to know what this statistic has to do with the structure of the pedigree. So let's suppose the recombination is Poisson, right? No interference. Of course, and then we're going to measure lengths in genetic lengths, so that the density of recombination breakpoints is uniform with respect to length. But still, the sort of local recombination probability per base pair varies. I'm going to call that rho. So on the left here is a bit of pedigree. And let's suppose that we're looking at a particular site on the genome, and that we know that at that site, the most recent common ancestor lived some number of generations ago, and that the path these two individuals inherited that bit of genome along through the pedigree has total length t, okay? So given that information, and that recombination is Poisson, we know that the genetic distance, like to the right, until the next recombination, so that's a recombination that's occurred in any one of these T meioses, is exponential. That distance is exponential with mean T. So in this example, there's 8 meioses along this path, so it's going to be exponential with mean 8 in units of Morgans. Okay, so the probability that we have a segment of IVD between these two chromosomes that starts at position I is equal to the probability that there was a recombination in one of these meioses between I and I-1. That's rho I times Ti, times e to the minus L times Ti. So L is the length of the IVD block, or the length that we're looking for, and T is the number of meioses. So the chance that the next recombination is further away than L. Okay, so what that means, all right, so our statistic, the block length spectrum is just a sum over individuals, and a sum over, the total number of blocks is the sum over sites of the number of blocks that start at that site. So that means that we can write the expected value of the block length spectrum as the sum of that probability across all locations in the genome. And then there's this extra term because that looks a little bit different at the front, because we always get a recombination breakpoint at the start of a chromosome. Okay, so, right, sorry, and yeah. Okay, so so notice what this looks like. If we think of the TIs as being something, that actually happened, then what this looks like is sort of a transform of the distribution of the TIs, of the you could think of them as the coalescent times, or actually the lengths of the paths through the pedigree. Okay, so so if we sort of rearrange that, and we let nu of t be the empirical distribution of coalescent times, of path lengths through the pedigree between these two groups, weighted by recombination rate. That's what I've got here. So nu of t is if you picked a site on the genome proportional to recombination rate there, and then picked a random pair of individuals between x and y, and looked at what the total length of the pedigree, length of the path through the ARG between those two individuals of that site is, then mu here is that empirical distribution. Okay, so if we sort of wave our hands about the any blocks that start at the start of the chromosomes, right, that first term, then what we have here is that the expected value of the block length spectrum is given by this transform of the empirical distribution, like with respect to this kernel here. And because this is something that depends on the length L, this is a high-dimensional summary statistic of the empirical distribution of coalescent times, and therefore of the pedigree. Okay. Okay, so that is, now it's time for this slide. So I'm sort of presenting here a general method of computing, like in particular means and variances, but also other things, of population genetic statistics, sort of in terms of the realized ARG, or the realized pedigree. And I find this useful to help me get a handle on thinking about what these statistics mean, independent of the demographic model that you want to put on. Like, maybe you don't believe any demographic models, or maybe you are trying to do demographic inference, and what you want to know, like, what aspects of the demography are these statistics telling you about? And an application to this could potentially be designing statistics to distinguish between hypotheses. Okay, so thanks for listening, and to some folks for giving feedback, including some others that I've missed here, like Eric, I think. Yeah, I could take some questions.
That's very interesting. It's sort of reminiscent of like the coalescent itself. It allows you to sort of derive a lot of new things. Just go back through in a little bit more detail about how the transform actually works.
About how the what did you say?
Transform actually works. So
this one.
This yes.
So how about let's just take so if we just suppose that recombination rates are constant, okay, then nu of t here is the empirical distribution of coalescent times, or well, of twice coalescent times, okay. So so nu of t is the probability that if you pick a random location on the genome and a random pair of individuals from the two populations, that their coalescent, twice their coalescent time at that location is equal to t. Okay, so that's what nu of t is. Thinking of the pedigree, or thinking of the arg as fixed, nu of t is that thing, is that empirical, is that summary statistic of it. Okay, and so then to get the expected number of blocks of length at least L, so the thing on the left is a function of L, you convolve that distribution with respect to the discrete parameter t, because t is counting up number of meioses, with the kernel 1 plus t times big L minus little l. Big L is the total length of the genome, times e to the minus lt.
So where does that 1 plus big L minus little l come from?
So the 1 is from the 1 is from the start of the chromosome, right? So so if we just look at the expected number, like number of blocks of length L that that are at the start of a chromosome, then that's just, well, you have to sum over the coalescent time at the start of the chromosome and then multiply by e to the minus lt. And then this here comes from, right, because e to the minus lt is the probability that given there are t meioses separating the two, that the next recombination that happened in any of those t meioses is at least L genetic length, L in genetic units to the right.
Yeah.
And then t times L minus L is, let's look on the previous slide. So that's coming from, so the t is for the same reason. The t is the density of, given a site has coalescent time t, that's the density of new recombinations that could possibly begin a segment of IBD. And then you have to integrate over the genome, okay? But then to get a block of length at least L to the right of you, you have to be at least distance L, like little l, away from the end of the chromosome. So big L minus little l is the total amount of the chromosome that you can start a block of length at little l in.
Okay, I got it.
Okay.
Let's see. Yeah, there's still something I don't understand, but I don't know if I can. But that's great. So have you played around with other summary statistics that might be interesting?
Other summary statistics, like what did you say?
That might be useful.
Not so much. Well, yeah. So I've written down what the covariance, right? The genetic covariance that you use in doing, for instance, PCA, what that means, and I find that kind of helpful intuitively. And you know, when I'm presented with like a big long list of F4 statistics, then thinking about this just is helpful, helps me to interpret them. I haven't gone and tried to do something like inverting this relationship to find the empirical distribution of coalescence times like we did for the IBD length spectrum. But.
And to be clear, I mean, you're really like writing statistics, not as a way if you're on our ARGs, use this formalism to evaluate something.
Sorry, I missed like half of that. Could you say that again?
You don't happen to have headphones available?
I don't.
Okay. So you're thinking of this as a way to derive summaries, not as a way to like actually evaluate.
What do you mean? So I mean, I think an application might be to derive new summary statistics, but more immediately, I'm thinking of it as a way of understanding what the summary statistics that we have are telling us. So like, and I mean, the reason this is useful is because, you know, most of our intuition about summary statistic is coming from the Wright-Fisher model, from randomly mating unstructured populations, right? But then like a lot of the places we want to apply these things are in, you know, thinking about applied to like genomes across Europe or something, where the populations are distributed across space and very much not like a single randomly mating population or even a few populations connected by migration. And I'd still like to know what they mean, what they're actually telling us about demography, even if we don't have a model that we believe.
Okay, that's helpful. But I guess I was asking. Will you ever consider as we can get a posterior on ours, and then we can get out that posterior, or is that just crazy?
Well, I mean, our previous talk was about getting a posterior on ARGs under a model, right? Sorry, so what's your question?
Are you mostly thinking of this as a theoretical tool for understanding? Or are you actually thinking about integrating things out with respect to ARG?
Oh, okay, right. So, like, might this be useful for computation? where, so maybe you're thinking of this slide where I said, okay, like if you're doing demographic inference just with sequence divergence, well, you might as well just have a model on mean coalescent time rather than the entire darn arg, right? Yeah, but I mean, maybe that might be useful. It's not really clear to me how that it would be, right? Because like working out what the what you really want to do demographic inference on is like models of populations, not models of mean coalescent times, and so yeah, that's not obvious to me that it would be computationally useful in that regard, but I'm not sure.
Cool. Well, I don't see any other questions. And talk again is it March?
Well, thanks a lot, Eric.
Thank you, Peter.